You are standing at the center of a sphere that NASA estimates is about 92 billion light-years across. The universe itself appears to be about 13.8 billion years old. Those two estimates look impossible together. If light has had only the age of the universe to travel, how can the part we see be so much wider than that age in light-years? The short answer is that the light crossed a changing universe. The longer answer changes what the word distance means. Start with the unit. A light-year is a distance, not a duration. NASA gives the speed of light of 1 light-year is about 6 trillion miles. In a quiet, unchanging space, you could use a travel time and that speed to build a simple ruler. The universe is not quiet or unchanging. While ancient light was on its way here, the space between large, unbound regions expanded. The light kept moving locally at the speed of light. But the distance separating its source from us did not wait for the journey to finish. Imagine walking toward the front of a moving walkway while the walkway itself is being lengthened beneath you. Your speed relative to the strip can stay constant even while the total separation between the endpoints changes. The analogy is imperfect, because cosmic expansion is not a machine embedded in a larger room. But it exposes the mistake. Travel time and present separation answer different questions. So what does the 92 billion light-year estimate describe? It describes the observable universe as measured now, under the cosmological model used to interpret the expansion history. It does not say that one photon traveled across that full diameter. It says the material whose old light can reach us now occupies a much larger present-day region than the light travel time alone suggests. NASA puts the distinction plainly. Some of the deepest James Webb images contain galaxies that emitted their light about 13.5 billion years ago. Because the universe expanded while that light traveled, those galaxies are now much farther away than 13.5 billion light-years. A recently confirmed example makes the idea concrete. Webb observed a galaxy called MOM Z14 as it appeared only about 280 million years after the Big Bang. NASA reports that its light traveled through expanding space for about 13.5 billion of the universe's estimated 13.8 billion years, stretching toward longer, redder wavelengths along the way. You are not seeing that galaxy where it is now, in its present condition. You are receiving an ancient signal and using a model of cosmic expansion to connect the signal's journey with the source's present separation. Cosmology needs more than one useful distance because a changing geometry will not fit onto one ordinary ruler. Suppose you ask a simple question: how far away is that galaxy? You might mean how long its light has been traveling. You might mean the separation when the light began its trip. Or you might mean the separation cosmologists calculate for the present cosmic time. In everyday life, those answers are close enough that one word handles all of them. Across an expanding universe, they separate. Picture a grid painted across a flexible sheet. A pulse begins crossing the grid toward you. Every moment, it advances through its local patch at the same allowed speed. Meanwhile, new space opens between distant grid lines. The pulse never hesitates and never accelerates beyond its limit. Still, by the time it arrives, the source can be separated from you by far more grid than the pulse encountered at the beginning. Nothing in this picture needs light to cheat. The geometry does the work. This also explains why a distance attached to an ancient galaxy is incomplete unless you know what kind of distance the speaker means. A travel time statement tells you about the signal. A present distance statement tells you about the reconstructed universe now. They can sound incompatible only because ordinary language hides the changing grid. Once you separate those questions, the supposed paradox dissolves. What remains is stranger than a paradox, a universe in which the ruler has a history. That is the first answer. The universe can appear about 92 billion light-years wide because the space crossed by the oldest light expanded during the crossing. But why are you at the center of the observable universe? You are, in one limited sense. NASA defines the observable universe as the portion of the entire universe that can be seen from Earth. That makes Earth the center of our observational everything. NASA's John Mather describes the Big Bang as a misleading name if it makes you picture a firecracker at one place. The universe does not have a center in that picture. Expansion happened everywhere, not outward from one privileged location. An observer in another galaxy would build a different observable sphere around a different location. NASA's Ask an Astrophysicist archive explains that any observer, at any location, sees the same general expansion pattern. More distant galaxies recede faster relative to that observer. Nobody gets a throne. That is why the boundary is better understood as a horizon than a wall. The observable universe is the region from which signals have had time to reach this location during cosmic history. The horizon marks a limit in information. It is not a shell of material, and the estimate is not a claim that the whole universe stops there. The phrase observable universe always carries an unspoken final word, observable from here. That makes the observable universe less like a territory with a border. A place enters your observational history only when some signal from it arrives. Before that arrival, a theory may describe the place, but an observation from it is absent. The horizon sorts those two statements. This distinction matters whenever someone turns unobservable into non-existent. The first word describes access to information. The second makes a claim about reality. Cosmology can model beyond the horizon, but the model does not become a photograph merely because its equations are elegant. What, then, is the oldest light that has reached here? It is not light from a star. For an early stretch of cosmic history, the universe was too hot and opaque for light to travel freely across great distances. NASA says that around 380,000 years after the Big Bang, atomic nuclei captured electrons. The cosmic fog cleared, the universe became transparent, and light could finally travel widely. That surviving glow is the cosmic microwave background, the oldest light we can observe. Expansion has stretched it into a cold glow of about 2.7 Kelvin. Adapted across the sky. This means the farthest electromagnetic view is not a photograph of the first instant. It is more like the surface of the fog at the moment the fog cleared. Look in any direction and you meet ancient light released from a different part of that surface. You cannot use an ordinary telescope to see through the earlier opacity, because the barrier is not weak equipment. It is the history of the medium the light had to cross. The microwave background is not featureless. NASA's WMAP material, the seeds that grew into the galaxies visible later. NASA also reports that maps of this background show space to be flat, meaning Euclidean geometry works on cosmic scales within the precision of those observations. Does flatness tell us the total size? No. A surface can look flat across the part you can inspect and still leave its full extent unresolved. Measurements constrain the geometry we observe, they do not hand us a view from outside the universe. NASA says directly that science has no reliable estimate for the actual size or infinite. That uncertainty is not a missing decimal place. It is the difference between a measured horizon and the totality beyond it. Deep field images make that difference easy to forget because they feel so complete. In 2004, Hubble assembled a million-second-long exposure containing about 10,000 galaxies. NASA compares the patch of sky chosen for the original deep field to a pinhead held at arm's length. Yet a deeper image does not move the cosmic microwave background out of the way. Region. Hubble's deeper gaze revealed far, faint objects that earlier observations had missed. It cannot turn a region with no arriving information into an observation. This is the discipline behind the phrase observable universe. It separates what exists in the data from what may exist beyond the data. There is another complication. The observable inventory changes. NASA reports that cosmic expansion is speeding up. The evidence emerged in 1998, when it concluded that they were farther away than the slower expansion prediction allowed. Scientists use the name dark energy for the still unexplained cause suspected of accelerating expansion. If that acceleration continues, visibility is not merely a matter of building a stronger telescope. Some light emitted across a sufficiently widening gap will never arrive here. Cosmic history determines which signals can join our archive. The observable universe is therefore not a static glass ball filled with everything that exists. It is a causal record centered on one location, assembled from signals that crossed an evolving geometry. The 92 billion light-year estimate is the present width of that record, not the age of a photon and not the known diameter of all existence. Now return to the apparent contradiction. The universe appears about 13.8 billion years old. The observable universe is estimated to be about 92 billion light-years across. Ancient light did not outrun light. Its sources became more distant while their signals were traveling. We sit at the center only because every observation has an observer. And the horizon is not the edge of reality, it is the edge of what has been able to report back to us. Beyond it, the honest answer is not a number. It is that we do not know. That may be the strangest scale inversion of all. Astronomy can recover a cold signal from the early universe, measure how expansion stretched it, and reconstruct a history across billions of years. But the complete size of the room may remain unavailable from inside the room. Which part unsettles your intuition more, that travel time and present distance can disagree, or that the total universe may never come with a measurable edge? Leave your answer in the comments. Next time, we will follow expansion forward and ask which distant light can still reach us. Subscribe if you want to keep going past the horizon we can see.